Okay, let's go ahead and start. Does anybody have any questions before I begin? All right, so we're fast approaching the end of this topic. And so today what we're going to focus on is we're going to look at reaction pathways or the reaction mechanism. Now, if you guys remember, we said in kinetics we have two important goals. One, we want to look at how fast reactions proceed, and secondly, we want to look at reaction pathways. All right? And so up to this time, we spent a lot of time looking at how we determine the rate law. The rate law is related to how fast the reactions proceed. All right? And we said if you want to determine the rate law or the rate expression, there are two experimental approaches that we can take. If what you're measuring in the laboratory is rate versus concentration, then we know we can figure out the rate law by taking two equations and dividing one by the other. All right, so that's if you're measuring rate versus concentration. The other alternative is we can measure concentration versus time, concentration of reactant versus time. And if the second approach is where you're measuring concentration versus time, then what you do is you make three graphs. You plot concentration versus time, ln concentration versus time, and 1 over concentration versus time, and you find the plot that gives you a straight line. And from that, you can establish the rate law. Okay, so we've looked at that. Now we want to know, what do we want to do with the rate law? Why is it that we go through this process of trying to figure out what the order of the reaction is and try to establish what the rate law is? And the reason we do that is because we want to figure out the pathway the reaction takes. And the word that we use to describe the pathway is called the mechanism. So we want to understand the reaction mechanism. So today we're going to look at reaction mechanism. And so I've written down some short notes for you, and it's on the class website. You already have a copy of it. You can see that many reactions do not occur in a single step, but proceed through a series of steps. All right? Remember when we looked at Hess's law, we said that, you know, a reaction can take place in a single step, or you can have multiple steps. It turns out many of the reactions, the majority of reactions actually take place in multiple steps. And if you take an example, if you look at the overall reaction shown here, if you look at the overall reaction where NO2 reacts with CO, so that gives us the reactants. These are the starting materials that you start with. And it reacts to give us the products, which are NO and CO2. So when we write a balanced equation in that format, where you give the materials you started with and the products that you end up with, this is the overall reaction, where you look at the initial state, the initial substances that you started with, and then you look at the final states, which are the final products. All right? So that just gives you the overall reaction that took place. So the overall balanced equation tells us the reactants and the products and the stoichiometry, the relative ratios in which the reactants react to give you products. Okay? It does not tell us anything about the pathway or how the reaction occurs in steps. So in reality, if you look at the details of how this reaction takes place, in reality what happens is one molecule of NO2 reacts with another molecule of NO2 to give you NO3 plus NO. So the first step, if you look at that, can everybody look at that and tell me what is really happening there? You have two NO2 molecules giving you NO3. So what's happening? One NO2 molecule has given up what? An oxygen atom to the other. And so you see an oxygen atom being transferred to the other so that you have NO3, and the other one has lost an oxygen atom, which is NO. That's the first step. Now in the second step, you can see that NO3, now what does that do? It reacts with CO, and what is it doing? It's transferring that oxygen to CO to give you CO2. So can you see the difference between the pathway that the reaction takes place and the overall reaction? The overall reaction is when you take the two steps and add them up, you end up with the overall reaction. So very often in thermodynamics, when we look at initial states and final states, what we're looking at is the overall reaction. We're not looking at the mechanism. We call this a mechanism or the pathway, but we're looking at what we started with and what you end up with. And we do not look at the intimate details of what's actually happening as the reactants, the overall reactants, convert to products. Okay? So the series of steps are called the reaction mechanism. So the goal of kinetics is to figure out the reaction mechanism. The mechanism gives you the intimate details of how exactly the reactants convert to products. We're not just looking at what you start with and what you end up with. We're looking at the series of steps that lead to how the reactants convert to products. So do you understand the difference between the overall reaction that we've looked at before, which just looks at what is the reactant and what is the ultimate product, and a reaction mechanism which looks at the series of events that lead reactants to convert to products? All right? So the two steps. So we call this a two-step mechanism, and this is the first step, and this is the second step. So to understand a reaction, we must know its reaction mechanism. And one of the main purposes of studying kinetics is to learn as much as possible about the steps involved in a reaction. So when we talk about pathway or the mechanism, that's what it means. All right? So each step in a mechanism, so each of these steps in a mechanism is called an elementary step. An elementary step is directly caused by collisions of atoms, ions, or molecules. The rate expression for an overall reaction cannot be derived from the stoichiometry of a balanced equation, as we have kept emphasizing, and must be determined experimentally. So if you guys remember, overall, experimentally in the lab, when we measure, all we have at our disposal is what we start with, the initial state, which are the reactants, and the final products. And so when we look at reactions in the laboratory, what we're looking at is the overall reaction. We're not looking at individual steps. So when you look at the overall reaction, remember we kept emphasizing that when you look at a reaction, you cannot figure out what the rate law is going to be based on an overall reaction. It turns out if you are looking at a mechanism, and each step in a mechanism is called the elementary step. And so if you're looking at steps in a mechanism now, you can actually look at the coefficient in that mechanism for each step, and you can write the rate law based on the coefficients. So the order of the reaction actually corresponds to the coefficient. Is that clear? So that's the difference between the overall reaction you're looking at and individual steps within a mechanism. And each elementary step, so we call each one of this an elementary step. And an elementary step really looks at it at a molecular level. So what this means is that when we write an elementary step, in the first step, it means that two NO2 molecules are colliding. So you have two NO2 molecules colliding. The instant they collide with each other, one oxygen is transferred from one NO2 to the other. And then it breaks apart, and you have NO3 and NO. Now this NO3 now will go collide with a carbon monoxide molecule. And the instant they collide, you have an oxygen being transferred. Because remember, they have to come into contact if you're going to have atoms transferring from one molecule to another. All right? And so an elementary step always describes collisions between molecules. All right? So the first step, you have two molecules colliding. You have NO3, and then NO3, as it bounces around, will collide with a CO. So again, you have two molecules colliding, and you have an oxygen atom being transferred from one to the other. So because you're looking at, in an elementary step, because we're looking at molecules colliding, we call that a molecularity. All right? And it turns out molecularity refers to one step in a mechanism. So you have series of steps, and each step in a molecule is called an elementary step or molecularity. All right? And it turns out elementary steps or molecularity can be of three types. All right? We call it unimolecular, And a unimolecular one is where you have, this is a step in a mechanism. Remember, this is an elementary step. We're not looking at the overall reaction now. We're looking at individual steps. And if you have a unimolecular reaction, it means its reactant is only one molecule. So what happens is A goes to products. So now we're looking at a single step in a mechanism. And if one reactant in a single step goes to give you products, we call that unimolecular. And so if you want to write the rate for this, the rate equals K, rate constant K times A. So this is for that one step, all right? So this is one step in a mechanism. Now, if you have two molecules colliding, like the one that we looked at where NO2 and NO2 collide, now you have two molecules colliding, so we call that a bimolecular reaction. So if you have in a mechanism, if you look at a single step, and you have two molecules colliding, so you have A plus A giving you products, then we call that bimolecular because now two molecules are colliding with each other. And if you look at the rate of this, because it's a bimolecular collision, now the rate corresponds to only in a mechanism, individual steps in a mechanism, the coefficient in the balanced equation gives you the order. All right? So here, it's a bimolecular reaction. Now you can either have the same molecules colliding, or you can have two different molecules colliding like this. So if this happens, you can see rate is K, it's first order in A and first order in B, but overall it's second order. So it's still second order, and you can see that the rate law, if you have two molecules colliding, you always call it bimolecular, and a bimolecular reaction will always be overall second order. Yes?
How do you know if it's first order without any experiment value?
So we're going to figure that out. So her question was, how do we know whether it's first order or second order without experimental values? It turns out what we measure experimentally is the overall reaction. All right? Today, our goal is to take what we measure experimentally for the overall reaction and figure out how you come up with each of these steps. All right? So I'm going to talk about first kind of introducing you to the fundamentals, and then the goal is that experimentally measure the overall rate law. We're going to use the overall rate law to figure out the individual steps in a mechanism. Okay? So we looked at bimolecular reactions. So when we say bimolecular, what does that mean? Two molecules need to collide, and so you can only have two reactants there in an elementary step because you have two molecules colliding. Okay? Now, if you have three molecules colliding, it's called a termolecular reaction. Okay? So reactions involving the collision of three molecules. These are rare because the probability that three molecules will collide simultaneously in the right orientation is rare. Okay? So the third problem is that if you have three molecules colliding, it's very, very rare that you have, when molecules are bouncing around, that three molecules will hit at the same time. All right? And so even though we talk about termolecular reactions, in reality, they're not experimentally observed. Okay? Because, in reality, they're not observed because it's very difficult for three molecules to hit at the same time. But if you did have termolecular reactions, then what you have is this, three molecules colliding, giving you products. And that would be rate constant times A to the power 3, because you have three molecules colliding. Or you can have two species. So if you have A plus B giving you products, then rate would be K times its second order in A and first order in B. Overall, it's third order. Or you can have three species that are involved, three different molecules colliding, and that would give you products. And here, rate would be first order in A, first order in B, first order in C, but overall, third order. All right? So like I said, when we looked at figuring out orders of reactions, I said, you know, the common ones are first order, second order, zero order. All right? And so here we've looked at the fact that if you look at individual steps, what we commonly observe is either unimolecular, which is first order, or bimolecular, which will give you, just for a single step, it'll give you a second order. Okay? Now let's go back to our mechanism. All right? So we said that each individual step in a mechanism, you can figure out the rate. And if you're looking at each individual step in a mechanism, now you can look at the coefficient of the balanced equation to figure out the order of that reaction. Okay? So now let's go back to our mechanism that we looked at. And if you look at this mechanism, you can see that this is a bimolecular collision. And when these two molecules collide, what you have is you have a new species being formed that's not a reactant or a product. So if we're just looking at reactants and products, we won't see this new species that's being formed. And if you look at this new species that's being formed, it's formed in the mechanism and it's consumed in the mechanism. So if you look at NO3, NO3 is something new that is formed in this mechanism or pathway. And then in that itself, it's consumed. So if you look at the overall reaction, if you're just looking at reactants and just looking at products, you don't see this new species that's formed and consumed. So in a mechanism, if you have a new species that's formed and consumed, and it's not a reactant nor a product, we call that an intermediate. All right? So we say NO3 is an intermediate in this mechanism where it's being formed and consumed. All right? So does anybody have any questions up to this point? So we're looking at pathways, and the pathways looks at individual steps. Yes, go ahead.
So how do you get zero order on your?
We're going to take some examples. All right? So I'm going to show you some examples where we're going to look at zero order. So you're not going to see zero order in individual elementary steps, but I'm going to show you how that comes into play. Okay? And in fact, I'm going to take an example in class and show you how the zero order comes into play. Okay? So we've looked at intermediates, and we said intermediates are formed and consumed in a reaction. And finally, we want to see how does this fit in with the overall rate law that we apply. So if we look at this, we said in this mechanism, we are saying that there are two steps, step 1 and step 2. Now remember, each individual step will react at a different speed or different rate. All right? And so if you look at this mechanism, you can see that the first step is the slow step, and the second step is the fast step. All right? So what you have is in a mechanism, you have reactions taking place in sequence. And you have step 1 taking place, then step 2. And if you have 4 steps, step 3, step 4, you have multiple steps occurring. But can you see that overall, the slowest step is what's going to determine how fast that reaction proceeds. We call that the bottleneck. All right? It's much like if you have 5 lanes in a freeway, and let's say each of these 5 lanes is like 5 steps in a mechanism. And if everybody's driving at the speed limit, which is, let's say, 65, and there's no problems, the traffic flows smoothly. But then suddenly what happens is, let's say the lanes are closed, and the 5 lanes are now closed to 1 lane. So now what happens? To begin with, everybody's moving at the speed limit. But once you hit that bottleneck, now what's going to happen is how fast people proceed beyond that point is going to depend on how fast the cars are moving through that single lane. And so that single lane is now the bottleneck. That's the slowest step. Likewise, when you have multiple steps and you have one step, which is the slowest, the overall speed of that reaction is going to be determined by that slowest step, because you have multiple steps. Everything can go fast, but you have one that is really, really slow. And so overall, what we measure experimentally is the slowest step. Do you understand that? So the rate law that we measure, or the rate that we measure experimentally, is always the slowest step, because the slowest step is called the rate limiting step or the rate determining step. That's the bottleneck. That's what's slowing down the whole reaction. All right? So when we look at experimentally, what we're looking at is, experimentally when we measure rate laws, we're looking at the overall reaction. We don't see the individual steps. All right? So what we see is the overall reaction. And the overall rate that we measure experimentally always corresponds to the slowest step in the mechanism, because that's the bottleneck. So if I take this 2-step mechanism, and if I take the first step, which is bimolecular, and if I write the rate law for that, the coefficient is 2. So for step 1, rate 1 would be K1, which is the rate constant for the first step, times NO2 raised to the power 2 because it's second order, it's bimolecular. All right? Now the step 2 is this, and that rate corresponds to, again, remember the rate always depends on rate constant times the reactants. So the reactants here are NO3, it's first order in NO3, it's first order in CO. So the fast step has that. So can you see that what we measure experimentally will correspond to the slowest step? And so what happens is that if we carry out the experiment and look at this reaction, what we measure experimentally would be, this is what we experimentally measure. We say rate equals K observed NO2 raised to the power 2. So if we were to carry this out in the laboratory and measure the rate law, this is what the rate law would come out to be. All right? And this always corresponds to the slowest step, because remember the slowest step is the rate limiting step. And so in a mechanism you have multiple steps, all right? And among those multiple steps, the overall rate of that reaction is going to depend on the slowest step. And the rate law that you see in the slowest step is what we measure experimentally, because in the experiment what we're measuring is the overall rate, and the overall rate is going to depend on the slowest step. So if you were to go to the laboratory and look at this reaction, this overall reaction is what we're looking at. And if you carry out the experiment, we'll find out that even though you have NO2 and CO, the net result is that's actually zero order in CO. Remember, your reactants are NO2 and CO. So your general form of this rate law would be, so if I take this overall reaction, and can everybody look at this and tell me, I have two reactants, so my overall rate should be K times NO2 raised to the power M times CO raised to the power N, all right? But what we measure experimentally is this, and what comes out is, from this we know rate equals K observed NO2 second order, CO zero order, so that equals K observed NO2. So it's second order in NO2. So this is what we observe experiment. This is from experiment. Now, this is what we observe experimentally, and you can see that corresponds to the slowest step. The slowest step is this step, and that is rate equals K1 times NO2 raised to the power 2. That's what we observe as well. Do you guys get that? And so what that tells us is that now we can explain. So what we start is we measure the overall rate order that comes from experiment, and then we come up with a mechanism that's consistent with that, and the mechanism has to be where the slowest step corresponds to the overall rate law. Got it? So let's take another example of applying this. So here's another example that I put. So this is the overall reaction we're looking at. So 2NO2 plus F2 gives you 2NO2F. So this is the overall, it tells you the reactants that you start with and the ultimate products that you end up with. Okay? Now if you go to the laboratory and carry out this the experiment and determine the rate law, this is what we observe experimentally. And so to show that it's experiment, we say the rate constant is what we observe experimentally. All right? So what we observe experimentally is rate equals K observed. It's first order in NO2 and first order in F2. So it's bimolecular, and that is the overall. So now when you come up with a mechanism, what does that tell you? That the slowest step has to involve these two molecules colliding with each other. So that means that you have to come up with a mechanism where the slowest step is where one molecule of NO2 collides with one molecule of F2. All right? And so here is a possible mechanism where you have NO2 colliding with F2 to produce an intermediate NO2F and F. All right? And this will be the slowest step. Got it? The next step would be another molecule of NO2 colliding with F to give you NO2F, which is the product. All right? And so the first step is slow and determines the rate. And so you can see now the mechanism that I came up with is consistent with what I have observed experimentally. Okay? So it turns out that coming up with a mechanism is really a skill. It's an intellectual exercise, and it's a skill that you develop. But whenever you come up with a mechanism, you have to look at the overall rate law and make sure that you come up with a mechanism where your slowest step corresponds to what you see experimentally. Okay? So now, scientists do this all the time. So when you come up with a new reaction and you want to figure out what the pathway is. And so remember, you guys have, if you're a biochemist or you're a biology student, you've looked at enzymes. And did you guys understand, you've learned about the lock and key mechanism, where how enzymes function and that they function in a lock and key sort of way. All right? That is a mechanism. And how do we come up with that mechanism? It's exactly this way. You use kinetics. Kinetics is the only way to figure out the mechanism. But it requires a lot of experience. All right? So how does one go about deducing the mechanism for a given reaction? The first thing you do is you go to the lab and you measure the experimental rate law. So you either measure rate versus concentration or concentration versus time and use the integrated rate law and make 3 graphs and figure out what the rate law is. All right? So that's done by experiment. Yes?
Does it matter that there are 2 moles of, oh, no, mine's.
Got it? Okay. So, and so the first step is to experimentally determine the rate law. All right? Now the next step is then using chemical intuition, one constructs all the possible mechanisms that are consistent with this rate law. So now you have to just brainstorm, and you sit there thinking of every conceivable possible way where the slowest step is going to correspond to the overall rate law that you observe. And this is just coming up with many different mechanisms. All right? Then what you do is you carry out, so you list out potential mechanisms. You can write to 5 to 6 different mechanisms. All right? Now what you do is you further carry out experiments to see whether you can eliminate some of them. One way to do it is if you can in situ measure the intermediate. If you can measure the intermediate, remember the intermediate is formed and consumed. Sometimes the intermediate forms so fast and is consumed so fast that you can't experimentally see it. But there are other ways where you can, it hangs around long enough that you can actually measure and use different techniques to see whether there's an intermediate being formed and consumed. And stuff like that. So you do further experiments to rule out some of those. All right? In the end, what I want you to remember is a mechanism can never be proved absolutely. And one can only say it is possibly correct. All right? So you can never 100% prove that there's the mechanism. Because remember, these are individual steps, and there's no way to see each individual step separately in the laboratory. Do you understand that? So it's purely an intellectual exercise, but you can say that in all likelihood, this is the best mechanism that you can come up with to explain that. Okay? Yes, go ahead.
So if you didn't write in the next to the 2 steps, the slow step and the fast step, we would be able to deduce from the
Yes.
observed which one's the slower step.
Yes. So you look at the overall one that you measure, and then you try to see which one it would fit, and that has to be the slowest step. Got it? And so the way that I'm going to do this is because it requires a lot of skill to come up with mechanisms. And if this is the first time you're seeing this topic, it's virtually impossible for you to come up with a mechanism. All right? So what I will do is that I have put up a worksheet on the class website, and if we have time, I'm going to work this in class. But so here is a worksheet that I put up. And so it's going to get you to figure out the rate law and take you through each step. And lastly, what I'll do is instead of asking you to come up with your own mechanism, I'll give you like 5 different mechanisms. All right? Of those, 4 will be incorrect. Only 1 actually will fit what you see experimentally. All right, and so you can see there's one mechanism there, 2 is a second mechanism, 3 is a third mechanism. And what I will expect you to be able to do is if I give you several different mechanisms, I want you to pick the mechanism that is consistent with what you see experimentally. All right, I will not expect you to come up with your own mechanism because that, you need a Ph.D. for that. It requires a lot of experience. All right, and so it's not practical for me to ask you to come up with a creative mechanism. Does that make sense to everybody? But what I will expect you to be able to do is given 4 or 5 different mechanisms, only one will actually work and is consistent with the experimental data. Got it? So now you understand why we went through this whole process of trying to figure out what the rate law, the overall rate law for a reaction is. And we said when we look at the overall reaction, because that's what we have when we start with, you cannot look at the balanced equation to figure out what the order of the reaction would be. All right? But once you figured that out, now when you look at mechanisms, now we know that each individual step in a mechanism, actually the coefficients in the balanced equation actually gives you the order. So what you do is for each mechanism, you take each step and write the rate law that corresponds to that step. And then you know that the slowest step, the bottleneck or the rate limiting step or the rate limiting step has to correspond to what you see experimentally. All right? Any questions up to this point? Now what I want to do is I want to kind of relate this to equilibria as well. So we're going to look at kinetics and equilibrium, all right? Because there is a relationship between kinetics and equilibrium. And so if you look at kinetics and chemical equilibrium, and let's say that we're looking at, consider a elementary step in a reaction mechanism. And we're going to just consider one step in a mechanism, okay? And let's say we're looking at NO plus O3 in equilibrium with NO2 plus O2. All right? So up to this point, we've looked at reactions that proceed only in one direction. When we deal with equilibria, you can see that equilibria deals with reversible reactions. All right? There's a forward reaction, and because there's a rate constant associated with the forward reaction, we're going to call that K sub 1. And there's a reverse reaction, and the rate constant associated with that, we'll call it, oh, let me not put it that way, let's put it this way. So can I rewrite that, please? So K negative 1, all right? And that is to distinguish, so let's say this is one step in a mechanism, and let's say this is the first step. So if it's step 1, because it's step 1, I'm going to call the forward rate constant K1, and for the reverse direction, I'm going to call it K sub negative 1, which is the rate constant for the reverse reaction, because there's two reactions going on. So if I take the forward rate, remember this is an elementary step, so I can look at the balanced equation to figure out the rate law. So forward rate, for the forward reaction, rate will equal, let's call that rate 1, would equal the rate constant for the forward reaction. Remember, the rate constant always depends on the concentration of the reactants, and it's first order in NO and first order in O3. Okay? Now if I take the reverse reaction, and let's call that rate negative 1, now the rate constant for the reverse reaction will be K sub negative 1. Now for the reverse reaction, which are the reactants? The products are the reactants for the reverse reaction. So the reverse reaction takes place this way, and therefore the rate law for the reverse reaction would be NO2 times O2. All right? And we know that at equilibrium, rate of the forward reaction equals the rate of the reverse reaction. That's what it means when we say a system is at equilibrium. We said the rate of the forward reaction and the rate of the reaction are the same, and that's why the concentrations of reactants and products don't change anymore. So because this rate 1 equals rate 2, I can say K1 times NO times O3 equals K negative 1 NO2 times O2. And if I rearrange this equation, you can see that if I take the concentrations of the products raised to the power of their coefficient divided by the reactants taken to the power of their coefficients, this really equals the ratio between the rate constants, which is actually the equilibrium constant. All right? So if you want to relate the equilibrium constants to rates, it's actually a ratio of the rate constants. The equilibrium constant is a constant, and that is the ratio of the rate constant for K. Equilibrium constant is K, capital K. All right? And if you look at that, that's really the ratio between two constants, which is the rate constant for the forward reaction divided by the rate constant for the reverse direction. Does that make sense to everybody? So now let's take an example of a mechanism where we have an equilibrium involved as well. So let's say that we're looking at this reaction. So I'm going to give you one example of a reaction where not only do you have just a regular reaction taking place in a mechanism, but you also have an equilibrium involved. So let's take this example where the overall reaction is 2NO plus O2 giving you 2NO2. And the experimentally measured rate law is rate equals K observed. This is the rate constant that we observe experimentally, is second order in NO2 and first order in O2. All right, so one way to explain this, one possible mechanism that can explain this is, in fact, if your mechanism just took place in one step. All right? You can see that if the overall reaction is also an elementary step, in other words, it's a one-step mechanism. Can everybody see that? If this is an example where this reaction took place in one step, and therefore the overall reaction is the same as the mechanism itself, which is a single step, you can see it's second order in NO and first order in O2. All right? But that's unlikely. If you want to come up with an experiment, one possible mechanism that has been suggested for this is this, where you have NO plus NO giving you N2O2, all right, where this is K1, this is K negative 1, and this is, we call it fast equilibrium. So this is step 1. And step 2 of this mechanism will be now this intermediate that's formed, N2O2 plus O2 equals K2, which is the rate constant for the second reaction, giving you 2NO2, and this is the slow step. All right? So if you add these two together, you can see this intermediate will cancel out. So what you end up with is 2NO plus O2 gives you 2NO2. So two ways in which you can explain this experimental data is say that this is actually a single-step mechanism, all right, where it takes place in one step so that the overall reaction is actually just one single step in a mechanism, and it's a single-step mechanism. Or you can explain it by a two-step mechanism. And in this case, you have the first step where you have a fast equilibrium followed by a second slow step. Okay? So now we have to derive an expression that fits what we see experimentally. This is what we see experimentally. So I need to derive an expression that explains this. And so we start with a slower step. My slow step is this. And I know that the rate equals K2 times its first order in N2O2 and first order in O2. All right, so the slow step has an intermediate. Can you see that? I took the slow step and I'm looking at the slow step and I'm writing the rate law that corresponds to the slow step. Yes, go ahead.
I have a question. How do we know that the slow step reaction is a second order reaction?
Is second order?
How come it's a 1 and 1?
You mean this step where there's one of this and one of this?
The slow step.
Yes. The rate law is first order because the coefficient is 1. The balanced equation, the coefficient is 1, so it's first order. Do you see that? So a single step in a mechanism, the coefficient in the balanced equation corresponds to the order with respect to, and only for a mechanism, only in an elementary step you can do that. Okay? But can everybody see this is not complete, because if you look at the rate law for the slow step, there's an intermediate there. Experimentally, can you measure intermediate? No. Experimentally, what you measure is the reactants that you start with. Can everybody see that? So that means I have to replace the terms with intermediate, the term that represents the intermediate, with terms that represent reactant. Okay? And how can I do that? I can go to the equilibrium constant, and now I have, this is a reactant, so we're okay. But that one, but if I go to the first step, remember that is an equilibrium, and I know K equals N2O2 over NO squared. Can you see that? Because this is an equilibrium, this is the law of mass action that tells me the equilibrium constant. Okay? Now, if I rearrange this, can you see now I have a term for this intermediate, which is K times NO squared. All right? Now I'm going to place this over there. So if I take this and replace it, now you can see rate equals K2 times a constant, equilibrium constant, times NO squared times O2. And therefore rate equals K observed. Can you see? This is what I see experimentally as well. So I can come up with a two-step mechanism. All right? But now my K observed is actually K2, which is the rate constant for the second reaction, times the equilibrium constant. Remember, it's a constant times constant is going to give me a constant. Did you guys get that? So both of those are consistent with the rate law. So it could be a single step mechanism where it just takes place in one step, and the whole reaction is just one elementary step, and it's a single step mechanism. Or it could be a two-step mechanism, but if you want to write a mechanism that is two steps, then you'll see the formation of an intermediate, and that intermediate is being consumed, but then you can overall derive an expression that also fits what you see experimentally. Can you see that? So we can come up with two mechanisms that are consistent with what we see experimentally, and so we need to do further experiments. So it turns out it's the second mechanism is what really happens. And the way you can check that is to see the formation of that intermediate N2O2 being formed and disappearing as the reaction proceeds. Do you guys see that? So once again, I'm giving you the mechanisms. It's very difficult for you to come up with a mechanism on your own. All right? However, if I give you a mechanism, and if you look at the homework that you are getting, the online homework as well as the homework problems that I picked from the textbook, you'll see in all those cases there are 4 different mechanisms, and you're asked to pick the one that fits what you see experimentally. Okay? Now, in the last couple of minutes, I want to show you how this whole thing is applied. Okay? And that's what that worksheet that I have put on the class website, and you can print it out. I would like you to work this out because it kind of explains the process as you go along. Okay? So let's look at this. So to begin with, consider the reaction. So we're looking at the overall reaction, and the overall reaction is given at the top. And the overall reaction we're looking at is SO2 plus O2. Let me straighten that out. What you're seeing is 2SO2 plus O2 giving 2SO3. So that's the overall reaction that you're looking at. Okay? Now, the following data for kinetics experiment were taken at 25 degrees Celsius. So can you see what kind of measurements are we making here? Are we using the integrated rate law, or are we using the rates versus concentration? Can everybody see rates versus concentration? That means that you have to take two equations, write the rate law, divide one equation by the other, and then figure out the order with respect to each one. So the first step is find the order with respect to each reactant. All right? Now once you've got that, then we've worked problems where you can determine the rate constant, determine the value of the rate constant, include the units. Next, calculate the initial rate of the disappearance of O2 in experiment 4. So if you can figure it out, if you figured out rate constant K, and you figure out the order with respect to each one of those, you can figure out what that question mark is in line 4. Okay? So let's quickly start by looking at A. We may not get through the whole thing. We'll complete it next time. But I do want to go through an exercise of how we build up and figure out the mechanism. Okay? So let's start with this. Find the order with respect to each reactant. So we start with all the information that's given to us. And we'll start by looking at the balanced equation. Can everybody write down the overall rate law, the general form? So we don't know exactly what the order is. So use Mn, and what would the rate law look like? Can everybody see? Rate should equal a rate constant K. What are the reactants for this reaction? We have SO2, let's say raised to the power M, and O2 raised to the power N. And can everybody see that in this we know the concentration of rate, we know rate, SO2, O2 concentrations. What we don't know is K, M, and N. In that table, concentrations are given and their corresponding rates are given. So if we have three unknowns, how many algebraic equations do we need to have to solve for it? We need three equations. And you can see there are three sets of data given. All right? So we'll start with the first one. The first one would be 7.2 times 10 to the negative 5 moles per liter per second equals K, concentration of SO2 is 0.1 molar raised to the power M, concentration, which is 0.1 molar raised to the power N. So that's one equation. Second line is 2.9 times 10 to the negative 4 moles per liter per second equals K. Now it's 0.2 molar raised to the power M times 0.2 molar raised to the power N. That's equation 2. If I take the third equation, it'll be 6.5 times 10 to the negative 4 moles per liter per second equals K times 0.3 molar raised to the power M times 0.1 molar raised to the power N. The third equation. So I have three equations. Now, the ones that I want to pick to start with is the ones where one of the concentrations are the same. So look at those three equations, and which would you pick to start with? Which equations would you pick? Equation 1 and 3. Can everybody see that? Because that's the only one that has the same concentrations. All right? Now, we always, as a rule of thumb, it's easiest to start with whichever has a bigger number divided by the smaller number. So this is 10 to the negative 4. This is 10 to the negative 5. So I'm going to take equation 3 and divide it by equation 1. Okay? So that means I have 6.5 times 10 to the negative 4 moles per liter per second equals K times 0.30 molar raised to the power M, 0.10 molar raised to the power N. I'm going to divide by a smaller number, which is 7.2 times 10 to the negative 5 moles per liter per second, K times 0.1 molar raised to the power M times 0.1 molar raised to the power N. So you can see K and K will cancel out. 0.1 molar raised to the power N and 0.1 molar raised to the power N will cancel out. And so if you divide this by this, you end up with 9 equals, this is 0.3 divided 3 raised to the power M. So what do you think M comes out to be? 2. Okay? So now that I have that, now I have to turn. So I've looked at these two, and these two will cancel out. So now I need to use these two to figure that out, the next one out. Okay? Now, we don't have the same concentration, but it doesn't matter because we already figured out what the order is, so we can put the order in there, okay? So now what I'm going to do is I'm going to figure out n, I'm going to divide 2 by 1, all right? So 2 would be 2.9 times 10 to the negative 4 moles per liter per second equals K times 0.2 molar raised to the power m times 0.2 molar raised to the power n. Divide. Now we figured out that m is 2, so I'm going to put square there. Okay? So that will be squared. And I'm going to divide by 7.2 times 10 to the negative 5 moles per liter per second equals K times 0.1 molar squared, because it's second order in SO2, which is m. And this would be 0.1 molar in n. Okay? So K and K will cancel out. If you look at this, this comes out to be 4 equals, over here I have 2 raised to the power 2 times I have 2 raised to the power n. Okay, so the number here is 4. So this is 4 already. 4 is taken. So what does n have to come out to be? 0 order, because anything to the power 0 is 1. Can you see that? So n is 0 order. So that means my rate law is what? My rate law would come out to be, so that's the first step, figure out what the rate law is. And the rate law would be rate equals K times SO2 squared, because it's 0 order in O2. So the experimentally observed rate law is this. All right? Now, can I ask you to complete the rest of that sheet, because it takes you step by step in all the kinds of problems that I expect you to be able to do. And finally, see whether you can figure out what the mechanism is. Okay? So we'll stop there for today.